Imagine a formula so powerful that just one term gives you 8 correct digits of pi. 2 terms, over 15 digits. No supercomputer, no tricks, just pure math, discovered over 100 years ago. Most formulas for pi are slow, painfully slow. You keep adding terms and barely gain accuracy. But Ramanujan found something completely different. He didn't just discover a formula, he discovered a blueprint for generating insanely fast ones. At the heart of it is this structure. Don't worry about how scary it looks. What matters is this. This is a machine. You feed in 3 numbers, A, B, and X, and out comes pi. So how do you pick A, B, and X? This is where Ramanujan does something genius. He doesn't guess them directly. He picks a single number called D, and that one number determines everything. Ramanujan chose D equals 58. Why 58? Because in a deep area of math called modular theory, 58 sites in a very rare category. It's complex enough to produce powerful results, but structured enough to simplify into clean numbers. Basically, it's a sweet spot. From D equals 58, we enter a world of strange functions. One of them is called the J invariant. You can think of it like a machine that turns complex numbers into massive constants. And for D equals 58, it outputs something tied to 396. That's why the formula contains 396 to the power of 4 in the denominator and 9,801, which is 99 squared. These numbers aren't random. They control how fast the series shrinks. Now comes the part that even mathematicians find crazy. To get A and B, Ramanujan used something called Eisenstein series. These are infinite sums, inside infinite sums, evaluated at a complex number involving the square root of minus 58. This should produce a complete mess, but instead, it simplifies perfectly. And out come 2 exact integers. A equals 1,100, 3b equals 26,390. No approximations, no rounding, just clean numbers. So why does this formula work so insanely well? It comes down to one bizarre phenomenon. E to the power of pi times the square root of 58. This number is almost a perfect integer. Not kind of close, absurdly close. And that tiny gap, that's what the series is correcting. When a number is this close to an integer, the error becomes tiny. And that means each term in the series crushes the error dramatically. That's why you get 8 digits of pi from just one term. Now let's try something different. What if Ramanujan picked D equals 10 instead? You can still build a formula, same blueprint, same structure, but now the magic disappears. The number e to the power of pi times the square root of 10 is not extremely close to an integer, so the error doesn't collapse as fast. That means each term gives fewer digits. You need more terms. The formula becomes slower, same idea, but far less powerful. So Ramanujan wasn't just calculating pi, he was searching for numbers where reality almost breaks, where massive exponential expressions land almost exactly on integers. And then, he built formulas that exploit that. But this isn't where the story ends. In 1988, 2 brothers took Ramanujan's idea and pushed it even further. Their names were the Chudnovsky brothers, and they found an even more extreme glitch. Their formula looks like this. Now this might look even more insane, but here's what matters. The number 640,320 is tied to an even stronger near integer effect. E to the power of pi times the square root of 163. Unbelievably close to an integer, closer than anything Ramanujan used. And because of that, each term of this formula gives about 14 digits of pi. That's almost double Ramanujan's speed. This is the formula used today to compute trillions of digits of pi. So the real idea isn't just about pi, it's about finding hidden numbers in mathematics, where everything almost lines up perfectly. Ramanujan found the path. The Chudnovsky brothers turned it into a superhighway. And somewhere out there might be even faster formulas waiting to be discovered.